Hello, sorry for the little interruption. So my name is Davide Gerosa. I was asked to teach gravitation waves from compact binaries. So this is a class, and that's Caroline. Hello, Caroline, who's going to be teaching some example classes for you and us later today. What did I want to say? So before I start, can I ask who you are? So can some of you or whatever say, what kind of PhD are you in? Is anyone here, okay, let's make me asking a question. Is anyone here in a PhD in gravitational waves? Okay, almost half. So have you ever had a formal class on gravitational waves already? Almost half. Okay, so that's why you're here. No, hopefully this is helpful for, so I'll do a cross-cut across, well, some core gravitational wave topics and then specifically on the emission from binaries. For those who are not doing gravitational waves for their PhD, what's your PhD about? Cosmology, okay. Anyone else who's not a cosmologist? Neither a cosmologist nor a gravitational wave? Star formation, okay. Well, stars end their lives as things that produce gravitational waves. So, astroparticle, okay. Gravitational waves are a particle. No, they're very classical, but okay. Anyone else? Okay, anyone who's not in their PhD, but either before or after their PhD?
I'm doing my master thesis.
Okay, so we got a couple of master students. Do you have master students here? A bunch. Okay, good. Okay, let's go, I guess. So let me copy down a website. So we put down some material. So these notes that I'm gonna use are at this address here. So it's on my GitHub profile. Davide Gerosa. How do I call it? Gravitational wave binaries. Florence, 2026. Okay, so if you go there, you'll find some of the material that Caroline and I put together. So the strategy for the class is going to be, so my own part, I'll do some more of the theory stuff at the board, and then Caroline will take over with some examples and problems and so on. The things I'll do, or at least the thing I plan to do, then let's see how far we go, but it's basically divided into four chunks. So today we'll do gravitational wave propagation. That's going to be part one. Propagation. Then part two is going to be about gravitational wave emission. Part three, which is really part 2b if you want, is the specification of gravitational wave emission to the compact binaries. So this is going to be about binaries. And actually, I would say half the class is going to be on point 3. As you see, indeed, there are actually 2 files on the website specifically on binaries. And then point 4 is going to be, well, the theory of gravitational wave detections. So I'm not a gravitational wave experimentalist, so I don't really mess around with mirrors and so on. But it's useful to figure out and understand a little bit what does it mean to actually detect a gravitational wave from a foundational point of view. What do we actually measure? What energy is dissipated where, and so on. So if I have time, I really want to do it because I think it's interesting, but hopefully I'll get to part 4 by the end of the class. And then Caroline will take over, and I think she has prepared, so this is Davide. Caroline is, I think she has prepared, so today is going to be about order of magnitude calculation, so figuring out from quick order of magnitude the things that we're actually measure. This is what are Fermi estimates, that's what these things are called. Then I think she'll cover a bit the writing down waveforms. So exploring a bit what I'm going to do on binaries, but more on the modeling of the signal, especially going into the Fourier domain and so on, which is the thing that we actually measure down the line. And then 3, I believe, is going to be a computational tutorial on parameter estimation. And I think for here, you'll need your laptops out, and you'll start decoding. Do you know when you're going to do it? Okay. So before Friday, make sure you have a laptop with, say, a Python distribution installed and things like this, right? So that you can follow the tutorial along. Everything else, I think, is going to be at the blackboard. My part is all going to be at the blackboard. Okay. Okay. So here is the plan. Let's see how far we go. We should have a break in between, so maybe at 9:45, 9:50, something like this. So if I get carried out, just wave at me and say we want a break. We need coffee. We're dying. Okay. So just okay. All right. So 1, gravitational wave propagation. Okay, so something I didn't say, but I should have said. So this class assumes some knowledge of GR. So I'm going to assume that you've seen GR in some form or another. Ideally, even understood GR. That's a big word. It's a big thing to say. I'm not sure I fully understand. I surely didn't actually fully understand the intricacies of the theory, but I'm going to take it for granted. So you've seen this thing, but the key dynamics equation of general relativity are the Einstein's fields equation that reads like this, where G mu nu is the metric of the spacetime, R is the curvature, meaning this is the Ricci tensor, this guy is the Ricci scalar, is equal to the stress energy tensor of the spacetime, T mu nu. So everywhere in my notes, G is equal to C and is equal to 1. So I don't want to bother with units. I'll put back the units when we'll do order of magnitude estimates and so on. But you can put back the units if needed. So sometimes I'm going to write down equations, so equation numbers or so, next to the equation that I write. They all reflect Maggiores textbooks. So which is my favorite textbook on gravitational wave. It's good that Leonardo left because he wrote a book on gravitational waves. But I actually use, it's good. It's not hearing me, so it's fine. I'm being recorded, unfortunately. So he knows what I'm saying. But I actually like, so Maggiore has a beautiful book on gravitational wave. The book is in 2 parts. All the theory that I'm going to do is in volume 1. So if I write down an equation next to what I write, they actually refer to Maggiore's book. So hopefully that gives you some guidelines to then if you want to go and look back at the book and find out. Of course, there's way more explanation than what I'm going to do in a few hours. Okay, so a core calculation in GR that you've probably seen is that of linearized gravity. That means assuming that your metric is flat, so Minkowski, plus a perturbation, mu, and then asking how is the perturbation behave, right? Well, the calculation goes that you define an auxiliary quantity, h bar, mu nu. You've probably seen this thing in class, so if not, stop me and I'll slow down, but which you remove the trace. And then you further impose the Lorentz gauge, as much like as you do in electromagnetism. You can always do that. You do that, and what you get is that the equations, so the Einstein's fields equation, so you start from here, you plug this thing in there, expands everything to first order in H, and what you find is that H bar behaves as a wave. So the Einstein fields equation becomes box of H 16 pi T mu. You get a factor of 2 during the calculation. And this is equation 124 in Maggiore's textbook. So these are the linearized, so these are the Einstein's fields equation, and this is the linearized version that you've probably seen, right? So one key thing to note here is that I've imposed the Lorentz gauge. And as we will see in a minute, the Lorentz gauge is not, it still leaves some freedom. There's still some freedom. So you can still change age around such that you remain in the Lorentz gauge. And we're going to use this freedom in a minute, right? Okay, so from this equation, it follows immediately that the partial derivatives of T mu nu is to be equal to 0, which is nothing but the conservation of energy and momentum, right? Okay, so I was saying, all up to here, I need to impose this equation here that is the Lorentz gauge, but that's not unique. So I can still move around in the Lorentz gauge without messing up with this equation. So we can impose further things, and let's impose that the trace of H bar is 0. I can further impose that one of the component is 0. No, oh, actually, this is equivalent to one of the component being 0, and then II being equal to 0. This thing is called the TT gauge, transverse traceless gauge. And it's the form where the equations simplify the most. And we're going to use it very, very heavily, right? I'll often write down HTT, meaning to say explicitly that I'm in the TT gauge, right? And we'll do at the end what it actually means physically to be in the TT gauge. For now, take it as a trick to simplify virtually all of the calculation that we're going to do. Okay. So you can define, if you have a quantity in the Lorentz gauge, say H, let's define an operator. I'm calling the majores call it the projection operator, that brings whatever tensor from Lorentz to TT. So it's going to be something like this, right? You can write down the explicit form of this operator, which I'm going to do now because we're going to use it later. There's really not much here. It's really a bunch of tensors or so on, and you can verify that with this expression you satisfy this condition here. So let me write it down because we need it later. So it's useful so that you have it in your notes. So it's defined in terms of another tensor P, JL 1/2 Pij PKL. This is equation number 136, where P, Pij depends on a given direction n, which is a normalized vector, Ni and J. Okay, not much here, really. Take it as whatever operator that brings something at rank 2 tensor from the Lorentz gauge to the TT gauge. That's really what it is. And if you need it, and we're going to need it later for one calculation, this is the explicit expression. Okay. What do I want to say? So yeah, one more thing that you've probably seen, right? But if you bring everything to the TT gauge, there are only 2 degrees of freedom of gravitational waves, which are the 2 polarizations, much like in light, in electromagnetism. So let's take a plane wave that propagate in, say, the z direction. So at any time t, my wave will look like, well, cos omega t minus z. Well, why a wave? Because the solution of this thing is a wave, right? I didn't even say it, but this is a wave equation. And the thing that you have in front is what encodes the polarization. It looks like this. So there are 2 degrees of freedom, which we're going to call H plus and H cross. H plus 0, 0, 0, 0, 0, 0. Okay. So if I give you, and sorry, this is in the TT gauge. Let's write it down explicitly. So if I give you the expression of the wave in the TT gauge, you want to read off the polarization, you just plug this coordinate, this component here. Okay? Okay, so this was, any questions so far? Hopefully you've seen these things before. It's just to lay down notations for everybody. Okay? So this was my recap of linearized gravity, right? Linearized gravity, now let's go on. Linearized gravity is not enough. And the reason is that it prevents we wouldn't detect the gravitational waves if we were to live in linearized gravity, right? So the effect, so what's happening when you detect a gravitational wave, or in general a gravitational wave, is that you dissipate energy somewhere, say in your detector, right? So for gravitational waves to be real, meaning I actually observe them, it means that there's a perturbation that comes, it deposits energy somewhere, and I detect that energy. Mirrors in LIGO or whatever, right? The vibration of a resonant bar or whatever it is, right? Now, if you work in linearized gravity, this is impossible to happen, right? So the background, my detector lives in the background, and if the background is forced to be Minkowski, well, it's not going to change, and there's no possible dissipation of energy. So this is really not enough for, well, you can do this calculation, but that's not how life works, I'm afraid, right? So we need something a bit more complicated than that, right? Because again, if gravitational waves don't carry energy, well, then it's just a mathematical construction. There's no meaning to reality, right? So we're gonna need something else. So I argue, linearized gravity here it's not enough. We need something. We need something more, and I'm on section 1.4 in the textbook, right? So we're gonna need to write my metric not just as Minkowski plus a perturbation, but at a given point in spacetime, some background plus perturbation. Right? So that's what we're gonna need to do. My detector is gonna live on the background. The wave comes in, the background changes, meaning there's some energy deposited in the detector. I detect that energy and claim a Nobel Prize or whatever, right? Now, this creates some issues though, right? So this is a background, and this is a perturbation on top, right? Now, this creates some issues. How do you actually separate the background and the perturbation, right? The business is pretty clear here, right? You get whatever metric, you basically take Minkowski out, and what's left is the wave. Here, well, it's much more dodgy, right? So what is actually the wave and what is actually the background? So the way to do it, or at least the way I understand best, is that of a separation of scales. So suppose that you have, your space-time, and then here I voluntarily do not write anything on the coordinate because it's just an end-wavy argument. Suppose that your space-time is, your metric is behaving like this, right? So you separate it into, well, a long wavelength component and a short wavelength component, and we're going to call one background and the other one perturbation, right? So we're basically going to separate the space-time in variation, in scales of variation, such that the wavelength of my wave is much smaller than the variation as scale of the background, right? Then I'm going to call this the gravitational waves. I'm going to call this the background where the detector lives. And then I hope that these things will bring energy to this and therefore claim a detection of gravitational waves, right? Or don't think about experimental detection, even, are gravitational waves real, right? Do they actually mean something or are they coordinate transformation? That's what you actually need to go through. So this will go, and I'll try to sketch it now, to a calculation that is similar to the expansions that you've probably done that brings you to linearized gravity in this form, but a bit more elaborate, right? So what we're gonna need is, so let's take the Einstein fields equation. So that equation that I have over there, and let's expand the Ricci tensor into, well, so imagine plugging this thing into the expression for the Ricci tensor. So the Ricci tensor depends on the metric and its derivative, Christoffel symbols and all that, right? You plug that into the Ricci tensor, right? And then you look at what it is, and it's going to be, there's going to be three terms, right? So there's going to be a term that is linear in, so a term that only contains G bar, a term that is linear in H, so this is going to be of order H, and a term that is quadratic, let's put a 2 here. This is going to be of order H square, right? Now, okay, which of the two frequencies or scales happen where? So this thing is clearly going to be of order L, right? So only the large wavelength or low frequency component is going to enter this guy. So here, this thing is going to contain only the G bar, and that's safe. Well, this thing is also okay, right? This thing is also only going to contain the wave. So this is only contain, sorry, the H. This thing is a bit more tricky because you can have two waves with different wave numbers that cancel each other, right? So this thing is going to have both the low and the high frequency component, right? So this term here is going to participate in both the background and the wave evolution, right? Now, what we want to do now is to average over a given length scale. So we're going to take this equation, pick a length scale which is intermediate, right? So this is much greater than the wave, but much smaller than the background, and we're going to average over a length scale L, right? Now this operation here would mean that all the high frequency modes, meaning the waves, will average out, while only the low frequency mode will survive, right? So let's write it down. Where are we? Okay, so my R bar mu nu, right? It's going to be what? I lost my train of thought. Right. So you plug this into the Einstein wave equation. So imagine now, so you take the Einstein fields equation, that thing, and you average over a length scale, intermediate length scale L bar. All the order H, all the R1 will go away because I'm averaging them out. What's left is going to be the thing that contains, well, either the G bar or both of them, because the G bar is also in there. And what you get is, well, so on the R, only R, if you take it this way, it's going to be R bar plus R2 that survives. And on the right-hand side, you're going to have the stress energy tensor, which I'm going to write this way. Averaged over the short scale, right? And this is number 122. 222, not millions, okay? This term here with the trace of T comes from that term that has the trace of R, which you can bring to the right-hand side. That's standard calculation in tensor manipulation in GR that you've probably seen already, right? Okay, now let's do some definitions here. It's going to be useful. So let's define, and these are going to be definition, like let's define T mu nu T bar such that G mu nu T bar is defined as this thing. And let's define little t mu nu as the other. Minus 1 over 8 pi and this is number 1 to 5. Now with this definition, these really take them as raw definitions for now. We'll see the meaning in a minute. With this definition, this thing, which is actually the Einstein field equation, becomes minus mu R bar this 130. Okay, so this is an important equation. Let's look at it for a minute. Right? And let's compare this with the Einstein's fields equation we started from, right? So let's compare that equation that I have right there in the corner with this one, right? Now, that says curvature is equal to energy, right? With the full metric G. Now, I brought it in a form that says again, curvature equal to, well, energy, quoted for now, right? Where all the terms that only contain the background are the bar quantities, T included. Remember, T bar, it's averaged here, so it only contains the background by definition. And all I have is an extra term, little t, that is this thing that contains the wave, right? So what I'm doing, I'm really bringing the Einstein field equation into an equivalent shape that has an extra term, that has background, everything background, which if you look at it right here, it's just the good old Einstein field equation, but with an extra term that now contains the gravitational waves. Now the interpretation is that this term here contains the energy of the gravitational waves. And that tells you, because it contains the R2 or whatever, it tells you how that thing interacts with the background. Any questions? Is it clear what I'm trying to say? Now, okay.
So if you take the background is G1 mu to eta mu, small t mu is just 0 then. You said that cannot carry energy.
That's right. I think it's right. I haven't done that calculation explicitly, but I think it's right. But I admit I haven't sit down to do it. If you reduce this calculation to G bar equal eta, would you get t equals 0? Little t equals 0. I think so. You don't think so?
You cannot, like, how do you define the length scale?
Yeah.
I mean, in the case of Minkowski.
You're gonna have plenty of derivatives of G bar that are gonna they're all gonna vanish. So I'm not.
No, yeah,
I'm not
my
sure.
question is, like, in the Minkowski,
Yeah.
you're saying, like, we can isolate the, like, low frequency mode, the background mode.
Yeah, well,
The other do with this, like, scale, intermediate one.
yeah. If you want in Minkowski, this L background is infinitely large. So I guess this framework is still verified.
Yeah, but the left-hand side is electrical zero.
The left-hand side, so this guy, that's right, there's no curvature in the background.
Because you're not doing the perturbation expansion once you put together, so you cannot.
You must be getting 0 equals 0, right? You must be getting 0 equals 0 somehow, because this is 0. We need to try and sit down and do it, but.
I remember that it's possible to not for the second order, so you can expand on
Okay.
the second order.
And still get energy of the gravitational waves.
I can check.
Okay.
Let me ask you a question.
Sure.
So, when the, like, scale separation is valid, is it always valid to assume that, like, the wavelength of your wave is smaller with respect to the curvature of your vector?
Yes, in all practical terms, I think. It's not going to be true in the vicinity of black hole binaries and so on, in the near space. But in the far zone where we actually put our detectors, it's very true.
So, like,
Okay, so something I've been a bit cheating here in a sense that, well, I've been calling this thing the energy of, but I didn't show, and then we'll do it in a bit, that can actually be interpreted as an energy, meaning it's a conserved quantity. That's going to be crucial, right? Otherwise I just messing around with terms and equations and moving tensor here and there, but is this truly a physical argument or not? So you're need to wait a tiny bit for that. Okay, so then next thing, and here, this is a really tedious calculation that I tried to do once and then got so bored that I put into Mathematica. But you can actually, so if you take that 125 and you plug in the Ricci tensor and all the derivatives and the Christoffel symbols and all that, you do get to this much, much simpler form. And again, I verified it with Mathematica once. But it's a very boring calculation. So I don't think it's worth doing it in any way. Okay. It involves again putting this thing in terms of the Christoffel symbols, then in terms of the metric, expand to order h square, because that's what you need to do, because there are two there, integrate by parts multiple times. You get to this expression here, so d mu h alpha beta, d nu h alpha beta. Okay, this thing happens to be in the Lorentz gauge by construction, because we started from, what is it? Because we put in, when you do the calculation, you put in the h in the Lorentz gauge. It also happens to be in the TT gauge. This can be verified with so verifying the conditions that I wrote down before, right? So so the zero component, why zero? Because I'm interested in energy. So now d becomes time derivative, right? tt, which is a dot, ij. Okay, and I can raise and lower indexes freely because I'm working at order h square. And this is already an h square, so any correction that comes on the raising and lowering indexes are not important to me. If you plug in now the expression for a plane wave propagating in the z direction, this is nothing but the sum of the two polarization. This is h plus dot square plus h cross dot square, which resembles a flux or an energy in electromagnetism, right? Which is actually nice. 135. Okay. Now, the right-hand side of 130, so these, sorry, the left-hand side, I meant. The left-hand side of 130, so this thing satisfies the Bianchi identity. This is nothing but Ricci minus Ricci scalar, right? If this satisfies the Bianchi identity, it means the nabla of that is going to be 0, which means the nabla of this is going to be 0, right? Now this is fair and square. If I am far from the source, so if I have a source of gravitational waves and I'm putting myself very far, right? There's no stress energy in the background, right? The background is the binaries that are generating the waves, right? If I'm very far from the source, in a region of spacetime where T mu nu background is kind of 0, right? So put yourself in the wave zone. It's an elegant way of saying the same thing. If that's true, well, this is also true. If I'm also far from the source, I can approximate nabla with partial derivatives, which means that these things becomes d mu t little t mu nu equals 0, right? Which is a conservation law. So this is the, my statement that this thing can be interpreted as an energy because it satisfies, at least in the wave zone, it is conserved. So it's a quantity that is conserved, and I can reasonably call it an energy, right? So it makes sense, I argue, to interpret this thing as the stress energy tensor of gravitational waves. It's going to be the physical interpretation that we put on this little t. Okay, let's try to compute the flux of this energy as it propagates away, right? What time is it? Need a break? Do you want a break? Is it a good time for a break? Well, five more minutes. Okay. I'm not going to do this thing in 5 minutes. I'm going to do it in 10. Do you prefer 10 minutes now? You prefer 10 minutes now? Okay. So we'll do the flux, and then we'll go into emission later. So I'm going a bit faster than what I thought. So if you have more questions or you want me to slow down, that's totally fine. Right? Now, when you prepare lectures, you never know actually how much material you and so on. But so feel free to interrupt. I'm not rushing through anything, right? Flux. Okay. So is this if this is a conservation law, right? So let's write it down again. But the T mu equal to 0. Let's suppose you have a source. Now it's emitting waves over a volume V, and let's take a little square area with normal direction, normal vector r. Now this thing, if I integrate it over the source, zero t0 0 di ti 0 equal to 0. Okay, now the energy over a volume V is going to be the integral of t0 0. Right. Energy. The flux d dt now is the minus because it's leaving the source, right? So it's going outwards the surface. Di t0i, where I use this equation here. So I substituted dt 0 0 with minus di t I0, which is equal. This is by Stokes theorem. I can integrate over the surface instead, right? T0r in the r component, right? This is the flux of energy in that's going out of the wave. This is Stokes theorem in here, right? Okay, then T0r, what is this guy here? I can get it from here, right? So this is 32 pi d0 hij tt dr hij tt. And this is 146. Okay, now a general statement about waves, you've seen in electromagnetism with Green's functions and all that, right? But my HTT, if it's a wave, if it's truly a wave, it cannot have any form that you want, right? It must depend on the retarded time. The property of the wave at a given time reflects the property of the source at the retarded time, because the wave has to propagate.
Sorry, silly question, but what is the 0r? What component?
It's the
Where is the time component, 0i or IC?
So I is so it's a Cartesian component, x, y, z. Yeah. R is the component along orthogonal to the surface. This is like when you do, I don't know, Gauss theorem in electromagnetism, right? So here I'm looking at, so if you're integrating over a volume, it's equivalent to integrate over the surface the derivative of the thing over the surface in that direction.
Normal to the surface.
That's right.
Okay.
That's right.
Because
Yes. If the sphere, your tessellation on the sphere is orthogonal to the sphere itself, and R is radial. That's why I'm calling it R. Yeah, yeah. No, it's fine. It's fine. It's fine. It's fine. Okay. So, any questions? Sure. No, I don't think so. Additional question. Does it transform as a tensor? I don't think so. Yeah, I don't think so.
No, it's
But the whole thing transforms as a tensor. Does little t?
do
you know?
Once average transform as a tensor because it's an average. Yeah, only with the.
Where do I have it? So I cancel it.
There is a proof.
Oh, there.
Average.
So that 125 transforms as a tensor?
Yes.
You can actually prove that?
Because of the
Okay.
average. Yes, because the terms that are non-transforming like a tensor are averaged out.
Okay. Oh, that sounds an horrible calculation. A totally horrible calculation to do. There's a proof. Okay. Over the short scale of the problem. So I actually don't know the proof. But he's saying there is. No, he was saying that the average procedure doesn't sound like something that preserves covariancy.
Yeah.
Which is a fair point, I think. I'm not sure.
No, the point is that if you make a general coordinate transformation, then you have, since this is not, without the averaging, this is not a tensor. If you don't put if you define the R2, it's not
So
a tensor, but there are extra terms. But it can be proved that the extra terms are
Go away.
arising from the transformation cancel with the average.
Okay. Did you get what he's saying? Okay. Okay. It sounds a very horrible calculation to do. It sounds a pain. I don't want to do it. Okay. So just to recap, the question was: is little t a tensor? If you take 125 and remove the average, it's surely not, because I'm cherry picking terms in an expansion from before. It looks like that, so Leonardo says there's a proof that if you take this thing without the average and expand it out, there's a part that changes as a tensor and a part that doesn't, and that when you average out, the things that does not change as a tensor, that transform as a tensor, gets to 0. It sounds like black magic, but okay.
Otherwise, you cannot give a physical meaning to this because only tensors have.
Is that true? Okay, well, this is we can discuss it later. This is chat for a coffee break, or what has or doesn't have physical meaning. So I was doing something much simpler than that, which was fluxes of H across a surface. So a wave, I would say, must depend on the retarded time, right? So this thing must be equal to some 1 over R, and then some function, ij, that depends on t minus R. There should be a R over C here, right? But then I'm not going to write it down anymore, right? This is saying that the wave at time t depends on properties of the source at retarded time. So we got to compute this guy over there, right? So dr h t t I j, it's going to be 1 over R dr f ij t minus R plus some stuff of order 1 over R squared, right? Where do I want to go? Where is it? Okay. But then, actually, if something depends only on T and R, dr of f, can try f. dr of f, it's going to be minus dt of f. ij, right? If something depends on t and r, if you want to swap t and r derivatives, you have to put a minus sign. So then dr, what am I doing here? ijtt is, well, I can lower indexes, who cares, because I'm working on order t, on order h, minus d0 hij these don't make sense. What's going on? Wait, I have a mistake in my notes. Let me try to find it. Let me try to find it. I have a mistake here. No, there's a minus sign that doesn't. No, okay. Up to here, it's okay. Up to here, it's okay. If you then, so my note says, $135 plus 146. There's a minus sign that doesn't work, because what we need to get is that T0R is equal to T00. Therefore, that thing becomes dA T00. But I can't find the minus sign right now.
In the calculation for the flux, you not skip one minus sign. That there's a minus sign because you're going out.
Maybe.
You also pay one minus sign from the changing derivatives. For the slope.
Okay. So what needs to happen, I'm missing a minus sign right now. What needs to happen, DET is equal to minus dAT00. So, but if I put T0R, now T0R, I need to get T00. If I flip a T derivative into an R derivative into a zero derivative, oh, you got it? Maybe I shouldn't.
But no, you have another minus sign from changing the derivative. So two minus signs.
Okay.
The minus sign in front of the integral, surface integral. Because you have one from the conservation law. Conservation law gives you one minus sign, but going
So yeah, I think you're right. So this,
There should be a minus in the top line.
the minus here,
these two
this guy,
the next one.
this guy is a plus.
The previous one as well, both of these.
Both of this.
Because you have two minuses, right?
I don't think so. No, there is a minus, but I think it's correct there is a minus. So why you don't want the minus there?
Because you want. Okay, so let's go with the calculation and then let's see.
It's negative. I mean, T0R is positive, and the energy of the system.
So now this T0R is gonna be minus T0R, right? Because if I oh, that's where it is. That's where it is. If I'm raising a zero index, I need to change the sign. That's what it is. So this is plus the 0 ij. Okay, I found it. Okay, now life is beautiful again. Okay. So this guy, this is a space component, so the signature of the metric is plus, so I can lower this index, but then if I'm raising this, right, so this gets a minus sign here, right? Okay, so now this is beautiful again. That means that, so if you put now this equation, 135 plus 146, you get that T0R is equal to T0, 0. I plug that into there, and I get the flux d dt is equal to minus dA T0, 0. And this is 151. Okay? Yeah, we made it. So, no, let me finish. Let me finish this thing. Then I go to the other file. Sorry. Yeah, I told you it was going to be a bit longer, but okay. Now there's a minus sign here, which makes perfect sense. The flux is going. It's decreased. The energy of the source is going down because okay, I'm losing energy. Now, yeah.
Are you raising with respect to G bar? It's one.
No, I think here I'm doing it in linearized gravity.
So we close.
I think so. Sorry for the inconsistency, but that's what's happening here, right? I think you can do it in full. It becomes a full post-Newtonian theory at that point, right? But yeah, I am operating in linearized gravity here. Okay, let's have a break. I need a break after this minus sign thing. Even if I want to finish something, I need a break. Okay. Okay. Should we go? Okay. The coffee break is at 10:45. What time is the coffee break? 45. Okay. All right. Okay, I found my minus sign. We were down there. That's the flux. So the energy of the energy inside this box is going down this way. Now the energy carried by the wave is minus that, right? So I need to put that back. And let's do it by unit area. Now the energy carried by the wave by unit area and time.
What is the order of magnitude, not the order of magnitude, but how is like this background field related to eta mean? I mean, is it like very large or like order 1 or order h? I mean, because I suppose here you are using order small h as your expansion parameter. So how does it like compare with?
I think G bar is over the, you should think of G bar being over the unity, meaning that you get, you have small deviation out of flat, and H being much smaller than 1.
H being smaller than 1. And then how are you allowed to sort of switch from like raising or lowering from G bar to eta mean?
I'm not allowed, I'm cheating. So I'm carrying out this energy calculation in linearized gravity. It's very possible to do it in the full theory. You need the full post-Newtonian expansion of the theory, which is the topic for another day, right? So yeah, I'll be switching. So I'm inconsistently, well, proved you that gravitational wave carry energy, but then and argue that you need a formulation for that, but then quickly switch out of that formulation, use that thing inconsistently in linearized theory. Yeah, that's exactly what's going on. So we were chatting before. These things were understood fully as late as the late 60s or so, right? So this is, so gravitational waves were, worked out and proven and whatever by Einstein himself and then Landau and whatever, but the full understanding of where is the energy actually going, what's the background or whatever, came as late as the 1960s. So, okay, I was saying, so the flux of energy, and let me do it per unit area and time, is nothing but T00. And this is really where the energy interpretation comes in, right? So that T thing is actually related, albeit inconsistently, to the power per unit area, right? That's what it is, of the gravitational waves. Now this thing is 32 pi dot ttij dot ttij. I am 0, 0, so I need to take time derivatives here, which is it's related to my polarization content, right? For a plane that propagates along the z direction. $1.53. And that's, well, that's a really nice expression, right? So it's saying that the derivatives of the two polarization directly impacts the flux of energy carried by the wave, right? So ultimately, this is going to be the things that are going to impact our detector, with the response function of the detector and all that. But these H plus and H cross are the actual things that we measure. Let me write down a similar equation now. Let me integrate over A. So just write down the power. As an integral over solid angle, because we're going to use that later. Okay, so this equation here is the, if you want, the master equation for the flux. That you might want to note down and or remember.
Sorry.
Mm-hmm.
What is the stuff you wrote?
Numerator.
Omega. It's a big omega. Like,
GW.
no. On the right, numerator up on the right hand side.
What? Why is
For the integral you have a fraction, not to the
32?
Okay, on the numerator is
R. Sorry, that's a R. So all I'm saying is that the A, meaning the little area, the area element is R squared d omega. Sorry. And there was a pi missing, so that I spotted it. Okay. There's a bracket missing for sure, down here. Yes. You're going to start the average and then maybe even close it. Okay. Is that right? Is this equation right? It sounds right. Okay, this is an R, radial coordinate, right? Okay, now I'm not going to do the, so this is for the energy. I'm not doing the calculation. A similar calculation, you can do the same calculation for momentum as well, right? Using the TI components, right? And the result is the following. So the flux of momentum, of linear momentum in the K component, dt, it's an analogous calculation, R squared 32 pi d omega. It gets you to something like this. So instead of taking the dot here, you take dk. The calculation. Yeah, there's green light here.
Okay.
All right. Okay. So gravitational waves carry energy. That's the first message that I wanted to convey in my class. Hopefully it kind of makes sense. If not, we can discuss it. We can discuss it further. Any questions? Happy to pause for questions. Okay? Okay. Let's move on now. Now that we've understood that gravitational waves propagate, hopefully doing something meaningful, meaning we can measure, let's look at the emission, right? So, because I haven't specified what this H is. That's going to depend on what's emitting gravitational waves. In my notes that are that you find on the website that I wrote down at the beginning, this is now on PDF number 2, gravitational wave propagation emission. Okay. Okay. So to go through with these calculations, we're going to need even more approximations, right? So we were saying before of a coffee break, GR is beautiful, but as soon as you do something with it, meaning you approximate something, it becomes horrible. And that's exactly, I'm afraid that's what needs to happen right now. We need a non-relativistic limit, right? So we're going to assume a source that moves at a non-relativistic limit, meaning that the wave propagate in a way that is, the waves propagated at the speed of light, and they leave the system much faster than how the source can react to the emission of the waves themselves, right? So we need a non-relativistic limit, which it's going to be, so v velocity much smaller than c, which for me is 1, right? Just to get a feeling of what this means, let's take, I don't know, let's take a simple two-body problem in Newtonian physics, right? So you have, the kinetic energy of, say, the reduced mass is equal to g m over r, right? That means that v over c square is actually m over r in the right units, right? So taking a non-relativistic limit, that also means taking the separation of, for a binary system, the separation being much smaller than gm over c square, which the astronomers call the gravitational radius of a binary, right? R much greater than m. That's, the post-Newtonian expansion. This square here is also the reason why post-Newtonian terms, maybe you've encountered these things, are counted in halves, right? We say 1 pn, 1.5 pn or so, because of this square, precisely because of this square here. Okay, so let's go back to linearized gravity. So I'll do the calculation in linearized gravity, because again, doing it in the full theory requires a whole Pn expansion. So we are back to something that looks like this, right? Okay, which we're going to solve with Green's function. So Green's function means that, so solve an equivalent equation, box of G, such that this thing is a delta function. Delta over space time, right? And well, the Green's function, it's where the retarded times comes in, right? Is that a big one? Yeah, they're all super tiny. It's 4 pi. So I'm going to call x bar the space component, and x without anything the space-time component, the space-time position, right? t minus x prime minus t prime, where this thing is the retarded time. Okay, so when you solve this wave equation with Green's function, what you get is an integral over those, right? So, sorry, this goes away. This becomes in your h mu 16 pi t mu evaluated over x, where this integral is integrated over the source. So you have a source right, that contains your, well, it's going to be the mass quadruple, but we'll see it in a minute. The source of gravitational waves, the vector x prime spans over the source. And then I have a vector x where I'm observing from. This integral is done over the source, so I need to, basically what this is saying is that you need to integrate the stress energy tensor everywhere in the source with a weight that is given by the Green's function, indeed, which is where the retarded time comes in, right? Okay, so now let's plug this thing into here. Well, let me write it down this way. No, actually, let me write it down here because I need more space. We're gonna get 4 d x prime. Okay, where here I'm specifying that the stress energy tensor is evaluated at the retarded time and the position of the source. So this is space, this is time, and this is space. Okay, then let's okay, let's put this in the TT gauge. So I'm gonna use that projector operator that I've defined before. So if I stick a lambda on top in whatever direction x, this is equal to my HTT now. Ij at time, let's write it down explicitly. This is going to be HTT at time t and vector x, right? So now this is saying if you want the wave at time t and position x, so say down here, what you need to do is to integrate over the stress energy tensor over the source, weight by this 1 over r contribution, right? They're just saying, well, that's just the amplitude of a wave that goes down as 1 over r, really. And then you got to do this tensor business here to make sure that the result that you get is in the TT gauge. Why we want the TT gauge? Because then we want to connect to polarizations and all that, right? So we're going to carry through that that projector there, over there. Okay. Maybe there's some mistake in the, sorry, there's KL here. Sorry. KL here. Okay. Now, if I'm outside of the source, as our detector will be eventually, right? You can approximate. So this vector here is going to be x minus x. This little thing. So x, okay, let's say that you got a magnitude r and a direction n, right? So this little thing is going to be x prime dot n, right? So if I'm very far from the source, I can actually approximate x minus x prime with r minus x prime dot n. Right, hopefully this is, I'm approximating this vector here with this little one. Right. If I'm very far from the source, that's okay. So so this thing here, I can actually write it as, so the retarded time, I can actually write it as t minus r plus x prime n. Okay. All right. So, okay, right now I'm only saying I'm far from the source. We still need to put in the non-relativistic limit to simplify things substantially. Now, in order to do this, it's kind of easy if we very quickly go to the Fourier. That's actually, I find it easier to understand where the approximation. You don't have to, but I think it's the easiest way. I think it's the easiest way to understand it, right? So let's write down quickly the Fourier transform of, so my TKL t minus r plus x n x prime. So this is going to be in Fourier space V4 some Fourier modes, fourth, whatever. This is the Fourier transform, L omega. By the way, K is omega K bar. E to the minus, so omega t minus r. Okay, there we go. All right, so now omega is going to be the frequency of the gravitational radiation, right? And this thing is going to be of order, so the frequency of the radiation is going to be of order velocity over the typical velocity of the source over the typical size of the source. If you have a source of size d that moves at the velocity v, the typical frequency that this thing is going to generate is v over d. X prime, right, bar is the size of the source. So this thing is going to be of order d. So this term here, omega x prime n, this thing is going to be of order v, right? So if I take the limit v much greater, much smaller than 1, this means I can actually expand e to the minus I omega x prime n hat. I can actually expand this as e to the minus, so let's take the omega out. I'm going to have t minus r, 1 minus I omega. Something like this, right? Plus some corrections, right? Okay, so so the dominant term is this e to the minus I. That's equivalent to like completely neglecting this term here. The second correction carries a multiplicative factor in the Fourier space. Multiplicating by omega in the Fourier space is equivalent to taking a time derivative in the time domain, right? So you're now going back to the time domain, assuming I'm only keeping this term, that's actually equivalent to considering my TL SAR x prime. That's the dominant term. And then I'm going to take this guy. Let's write it down in components, but it's the same. X prime I and I dt. Where this derivative here, crucially, is evaluated at the retarded time. Okay, so now what we want to do is to take this thing at this approximation and plug it into here. I didn't write down the number of equation, but this thing was 311. Sorry, so that you find yourself in the book. So this thing is 311. Is that right? No, there was another. I had another one in between. Where did it go? No, that's fine. Okay. So now I want to plug this thing into 311. When I carried out that expansion, where I neglect this thing, I can substitute R in here. So okay, so now plug that into 311, and the result is something something very beautiful that looks like this. All these complications are going to go away in a second. Oh, long ones. Thank you. J K L, and let's call this tensor S, which I'm going to define in a minute. M other terms, all evaluated at the retarded time. And this is number 334. This S here that I've defined, so this is their definition. These are the moments of the stress energy tensor. Like the zeroth and the first moment of the stress energy tensor. Now this thing is, it's really beautiful. It highlights the expansions that we are making, right? So this is going to be the dominant term. This is going to be of order, well, d, there's a distance here and a time here, time derivative. So this is of order, this is going to be of order space over time, which is a velocity. So this is of order v. And this is of order v squared, which are going to be subdominant corrections, right? The dominant terms comes from here, which is where the quadruple formula is going to come from. That's where I'm going, right? You've seen the quadruple formula before, some of you at least. Okay, that's what's going to happen. that's what's going to happen now when you keep this term only. So crucially, I think the one thing to remember here, the details of the calculation, whatever, the one thing to remember is that it's moments of the stress energy tensor that appear, right? So the waves they depend on integrals of the stress energy tensor integrated just by itself or by the position x, which are these moments. Okay, now most of the literature rewrite this equation in a different notation. So let's do it so that we can find our way back to things that we. So that's already the answer, but let's write it down in a form that it's easier to interpret. So now we want to rewrite everything using mass moments. So let me define big M to be the T00 Mi Mij to be so this is going to be the mass of the system, the total mass of the system, the mass dipole and the mass quadrupole, and similarly for P. So Pi, this is D3T00. Pij is the same, but 0I xj and so on, right? Okay. If you write things down this way, many derivatives also go away. So for instance, m dot, let's compute m dot, so dm over dt. Right? Now this thing is going to be the integral T00. Now if I use, here I can use d mu, T mu nu is equal to 0. Di T0I. What do I do? Stokes theorem again. This is going to be over some volume, over some surface. And if I'm very far from the source, this thing is 0. I'm evaluating the stress energy tensor very far away from the source. This thing is 0, right? So this is interpreted as the conservation of mass, right? So similarly, I need to put a big caveat here, big asterisks. Remind me to go back to this in a minute, if I forget. So this is interpreted as the conservation of mass, and you can, with this expression, you find similar constraints. You find similar constraints. So we said m dot is equal to 0. You similarly find the m dot I is equal to pi. That's the momentum equation. The m dot ij Pij. That happens to be the derivative of the mass quadrupole, which is going to be important in a minute. P dot I is also equal to 0. That's the linear momentum conservation. And angular momentum conservation comes from if you take P dot ij minus P naught ji. This thing you can prove is also equal to 0 and is the conservation of angular momentum. Now the strategy, because these things have conservation easy things, the strategy now is to replace all the S's in here, which is right, but it's just hard to understand, with M's and P's, right? So that's really all that happens all that happens here. So what I need now is Sij. So it's going to be 1/2 Mij dot dot, which is the mass quadruple, and then S dot, S naught is KLM. So you need 3 derivatives of the mass quadruple here, Ijk plus there are some p's here. It's not important because I'm going to neglect it in a second, but let me write it down once and for all. Jik minus 2 Kij. Okay, who cares? It's not important. So the dominant term here is this guy, which is going to be this guy. That's the mass quadruple, right? The first subdominant correction, which I'm going to neglect in a second, it's in the S dot term, and that's going to call the mass octuple, this thing, and the current quadruple, this thing. And those are the first correction to gravitational wave emission, right? First correction to the quadruple formula come from mass octuple and current quadruple. Let's neglect them now and proceed with the quadruple, with the quadruple only. So if I am, so at the dominant, yep.
Maybe it's nothing, but are you sure about the indices you put, like in the second S dot solution? KLM, IJK, and then...
No, there's something off here. No, there's something off here, right? No, there's something off. This must be IJK. Okay, so it's equation 353. So you can 353. You can check it. I will need to check on the book. I suspect this is actually IJK. You're right. What I wrote doesn't make sense. I strongly suspect this is IJK. But I have it wrong in my notes as well. I will need to check. Sure. I can finish whenever. That's fine. I suspect this is IJK. We can check in the textbook later. In any case, I'm going to neglect this term immediately, right? I just wrote it down to say that these things exist. So, yeah. Okay. So let me write down the key equation for, and then we wrap up. So let's neglect these terms here, which are of order v and order v squared. So only look at the dominant term. That S is the derivative of the mass quadruple, which is. So let's write this down again. In some direction n, m dot KL, and let's write down that this is evaluated at the retarded time. Right? Okay, so this is important. This is saying that the waves in the TT gauge are the second derivative of the mass quadruple of the source, which is a statement you've probably heard before. Hopefully this is in context now, right? So if I want to compute, if I have a source, I want to compute how much waves they're emitting, I need to get their stress energy tensor, compute the second derivative of their mass quadruple, meaning T00 energy over xi xj, second, so quadruple, take 2 derivatives, evaluate it at the retarded time, and that's going to be the wave. In the TT, if you put this thing, that thing is going to be in the TT gauge, which is the thing that we then going to need to read off the polarizations and all that. Okay. Okay. So usually you yet another way of rewriting the same thing, again, because people write it in different way, but we can remove the trace from this quantity. So let's define Q. Again, this is yet another definition. There's no. So let's define Q to be Mij minus its trace. And Kk. Right? Now, this thing is, okay, let me write it down explicitly. It's going to be D3x. Xi, xj, r squared dij. Okay, now, if I now write down this expression here, right, so this is 2 over r, my lambda, ijkl, right? It turns out that when you contract this projection operator with the delta function, this thing is 0. That's in the properties of this projector operator that I wrote down at the very beginning, right? And that's why you want to define Q, because actually the trace part goes away when one brings it in the TT gauge, right? Operationally, from a tensor perspective, if you grab the properties of the projector operator and you contract it with the delta, you get identically 0, right? So this thing is actually equal to 2 over r jkl q kl t minus r, which I'm going to define, this is really a definition, as qtt. Guess why? Q tt ij t minus r. Qtt is the contraction of Q with the projector operator, which is identical to contracting M because of the property below. And this is H bar Tt. Okay? And I think this is a good time for, so this equation here, we got to here. We got to here today. Tomorrow we'll do, we'll get to the quadruple formula. That's really, we're really close, right? And then we'll start looking into binaries as well. Coffee break, I guess.